Hello, this is the video lecture for General Physics 2 for Monday, March 30th. I hope you all had a restful spring break. I know this is extremely weird. It's been kind of weird for all of us, hasn't it? But I want to give you a few reminders. This week, your homework for chapter 23 on circuits is due on Friday, April 3rd. Turn it in by 5 p.m. by email. Um, on Wednesday, during lecture and my office hour times, I will be on Zoom, and you can call me on Zoom and ask questions, or you can call me on my phone and ask questions. I'm not going to do Skype. Skype didn't work as well, so I'm working out Zoom. And then fairly quickly, after we finish chapter 24, we're going to have test 3. I'm not exactly sure the format of test 3, but we are going to have test 3 on after that on chapters 22, 23, and 24. And so I want to let you know that that's coming up. Anyhow, so our objectives here, our topics are magnetism, the magnetic field. There's a magnetic field just like there is an electric field. And then we'll talk about the relationship between electric current and magnetic fields. And then we'll be able to do some calculations. We'll be able to calculate the magnitude and direction of the magnetic field that is created due to current passing through a wire. And then we'll talk about how magnetic fields exert forces on charges, and how magnetic fields, since currents can influence magnetic fields, and it goes the opposite direction as well. Magnetic fields can exert forces on currents. And then magnetic fields can create forks or exert force on dipoles as well. And then we'll talk about magnets and magnetic fields. This is a pretty long chapter. We're going to be here for a little while. I'm going to try to keep this video lecture today under an hour. So we'll cover about the first half of the chapter. Okay. This is not your homework. I repeat, this is not your homework. This is from an earlier semester where I taught this class. So I will be giving you homework on chapter 24 on Friday. Okay, so magnetism is not the same as electricity. Okay, there is some very similar aspects of magnetism and electricity, but it's not the same force acting. Okay, magnetism is a long range force, so it acts on objects that are not necessarily attached. Okay, and we have two poles in magnetism. We have a north pole and a south pole. And like things repel each other, it's similar to electricity, but the pole that on the Earth that repels a known south pole and attracts a known north pole must be the south magnetic pole. And then there are materials that are magnetic attractable, non-magnetic attractable, and then non-magnetic, non-attractable. Okay. So if we had, let's say, a petri dish, and we had a cork floating in water on the petri dish, and we just laid a magnet on top of that, then the north pole of the magnet would orient north, and the south pole of the magnet would orient south. Okay, and the way that that works is much like a compass. You've just created a simple compass, and everything is related to the north magnetic pole and the south magnetic pole of the Earth. Okay, so if we put the north and the north together like this, then they repel. But if we take the north and the south and put it together, they will attract until they attach to each other. We can influence a compass with a bar magnet. If we have a strong enough bar magnet, then we can cause influences to a compass. Okay, and magnets are interesting. If I took a magnet that had a north pole and a south pole, and I sawed it in half, then it would create a new north and south pole, okay, on each of the subsequent magnets. Okay, and magnetic attractable materials will uh, attract non-magnetic attractable materials. These iron paper clips are not magnets, but they will attract. And so you can see that they can attract to the North Pole, they can attract to the South Pole. Here's a copper penny that also happens to be magnetic, so that attracts to the North or the South Pole of the magnet. Okay. Have something like plastic that is not magnetic, there's no effect. Okay, and so the magnetic field is just a magnetism that is created all around a magnet. So if I took a magnet that was fairly powerful, and I'll do this in the laboratory for you, then we'll have a magnetic field, and the magnetic field and then always points towards north. So if we look at the north pole of the magnet here, then the north pole of the compass is always going to point away. Okay. If we move it over to the south pole of the magnet, then the north pole is going to attract, and it's going to attract it. Okay. The strength of the magnetic field is proportional to the torque felt by the compass. This will move back and forth. Okay. And if the magnetic field is weak, then it's going to move back and forth slowly. If the magnetic field is strong, then it's going to snap back and forth rapidly. Okay. And so if we had some magnets, and I just took some iron filings that act like tiny compasses, then we would see that in the north magnetic field, then field lines would go away. And then in the south magnetic field, whoops, didn't mean to do that. In the south magnetic field, then they would go towards. Okay. And you see the little mini magnets here, the north pole is pointing away in each case. When I'm directly between the north and south pole, the north points away from north, south points away from south. And then when I'm over here on the south pole region, then the north on the magnet points towards the south, or the north on the compass points towards the south of the magnet. So it looks something like this. So the north is going to go away from the north pole, okay, and orient then towards the south pole. Okay. And if we have strong magnetic field, stronger magnetic field will be closer to the magnet, and we indicate that by larger arrows, because the larger arrows would then say this is the direction and the magnitude of the magnetic field. Okay. So if we draw field lines, then field lines are going to move away from north, and then they're going to move towards south. Okay. And the direction of the magnetic field at any point is just tangent to the field line. Okay. And where when the lines are drawn closer together, like here, towards the poles, then you would have a stronger magnetic field. When the lines are further apart, then you have a weaker magnetic field. Okay. So let's say you have a simple bar magnet, and like I said, I'll do this in the laboratory. Then you can create magnetic fields. There's a single bar magnet, and that will create a magnetic field. Again, the field lines are closer where the magnetic field is stronger. And then if you want to know the direction of the magnetic field, then you just draw tangents to the field lines. We take a close-up of that, then you can see how the magnetic field moves from north to south. And if we have two magnets that are facing each other, then they're always going to move from north to south, the field lines are. Okay. And then if we have two repelling magnetic fields, if we have north and north together, then the field lines are basically going to move very, very quickly away from both north poles. Okay, so let's just look at understanding. So let's say we have this magnet over here that is north and south, and we have a magnet here that's north and south, here south and north. Okay, and we want to see where and each of the labeled points in which direction A and E will encompass point. Okay, so if we look at A, this is pointing directly north to south, okay? And I would say that that's number 2, because the North Pole is, the compass is pointing as far away as it can from the North Pole of the magnet, so it's going to do that, okay? For B, I would say that is number 1. And number 1, then you would have the North Pole. The North Pole would be facing away from the North Pole of the magnet, and the South Pole would be facing towards. Okay, and then C, where you would have pointing up north and then pointing down south. Okay, I don't see anything that would be C, but I do see something that would be D, which is here. Okay, and D, you would have the south oriented towards the north and the north oriented towards the south. And then for E, where you would have magnetic field of 0, then that would be 0.4. Okay, because your magnetic strength would balance out, each of these north, each of these south, so those would cancel out. Okay, so we're always influenced by magnetic fields. Okay, here's a different type of magnet. This is a U magnet with a north and a south pole, and you can see the complex magnetic fields that are associated with that. Okay, here's a compact disc or DVD, and you can see that north and south are stored in different magnets. Okay, so different magnets along the disc itself. I'm sorry, this is a hard disk. This isn't a CD, is it? It's a hard disk. Okay, and so you would have to see where ones and zeros would be stored within the magnets. Okay, and the Earth itself has a magnetic field. Okay, and the south pole of the Earth's magnetic field is actually in northern Canada. Okay, we call that the North Pole. But north, because it's south here, then north is attracted to it. Because it's north here, and then south is attracted to it. Okay, and in the northern hemisphere, the Earth's field is vertical, and the components point down. Okay, and then when you get further away from the north magnetic pole, then the components then become less perpendicular and more tangent to the Earth. Okay, the south pole of the Earth's magnet, which we actually call the north magnetic pole for maximum confusion, is located near the north geographic pole of the Earth, and it does shift. The magnetic poles in the Earth are in constant motion. They have to do with molten iron in the core of the Earth. And the south pole has moved almost 500 miles, over 500 miles, 1,100 kilometers through Canada through the last century. And again, geophysicists believe that this is due to currents of molten iron in the core. And it also turns out that electrical currents can create magnetic fields. Okay, and this is where students often get confused with this, but electricity and magnetism are intimately tied to each other. They're perpendicular to each other. So we're going to talk about electric fields in conjunction with magnetic fields. Okay, so if we have a long straight wire, then that will create a magnetic field that goes circular around it. Okay, and depending on the wire, the current, then it can go clockwise or counterclockwise. If we have a current loop, then you can create a magnetic field where north will shoot through the loop, okay, where you can see the field line shoot through the loop. And then as we get to the edge of the loop and outer surfaces, then the magnetic field strength becomes less. Or we can have a solenoid. A solenoid creates a really, really strong magnetic field within the coils themselves. Okay, we can see that the electrical wire is coiled around. Okay, and so that creates a strong magnetic force. So if you have a magnetic component, you can cause it to move. Now, let's say you just have a straight wire. Okay, and here's our straight wire, and the currents are going up. Current is going up, and then if the current is going up, then the field is moving counterclockwise. If you take your thumb on your right hand and you have that be the current is moving up in the direction of your thumb, then your fingers curl around in a counterclockwise fashion. That's called the right hand rule. Okay, so when current is moving up, then the magnetic field is going counterclockwise. If the current is going down, so take your right hand and move your thumb so it's pushing down, then the current, your fingers curling around, or excuse me, the magnetic field, your fingers curling around, then go in the opposite direction. They go in a clockwise direction. So that's called the right hand rule. Okay, so right hand rule for fields, here is just you point your right thumb in the direction of the current. You wrap your fingers to indicate a circle. You wrap your fingers around the wire, and then your fingers curl in the direction of the magnetic field around the wire. Okay, so that's the right hand rule. When the vector is coming in or out of the page, vectors into the page are X's. Vectors out of the page are just dots. Current into the page is an X with a circle around it. Current out of the page is just a circle with a dot inside it. Okay, and so if we had current coming out of the page, then you use the right hand rule. Or going into the page, sorry, you use the right hand rule, and that would show you that now the magnetic field is moving in a clockwise direction. Okay, so let's take a look at this. I don't know why that's doing that. Okay, never mind. So let's take a look at this. So point P is 5 centimeters above the wire as you look straight down at it. Okay, and we want to find the direction of the magnetic field at point P. Okay, so what we do is we take our right hand, take our thumb, and we move it over to the right. Okay, and then we curl the magnetic field around, and you can see at point P where it's outside the page, then the current is actually moving down, or the magnetic field is actually moving down D. Okay, so it's going down from the page, or down on the page, because your right thumb is moving to the right, and if you curl your fingers around when they're outside of the page, then they go down. Okay, so here's a rough sketch of magnetic field wires. So the current in this case is going into the page. So you take your thumb and you point it into the page, and then your fingers curl clockwise. Okay, so the magnetic field lines are clockwise circles around the wire. Okay, magnetic field vectors are longer where the magnetic field is stronger, closer to the wire, and magnetic field vectors are then shorter when they're further away from the wire. Okay, so if we're down here where the magnetic field is strong, then we would have stronger magnetic field lines because we have a stronger magnetic field. Out here we have a weaker magnetic field, so the lines are smaller. Okay, if we have a loop, then the right hand rule still applies. Okay, in this instance over here, the current is coming out of the page on top and then going back into the page on the bottom. And so you just take your thumb, your right thumb, and you move it with the current going out of the page, and that shows that the magnetic field is moving through the loop from left to right. And at the bottom, it would do the same thing. It's going through the loop from left to right. If we look over here, and our wire is actually in the page itself, then if our current is moving to the left, then we take our thumb and point it to the left, and that means the magnetic field is moving through the loop out towards you in the page. Okay, so hopefully you're doing this all with your right hand. Your right hand's getting a good workout today, and that will help you understand the direction of the field due to the current. Okay, if you have a solenoid, then we can use the right hand rule on top. Current is going out of the page. Okay, and so the magnetic field is going through the solenoid or going through this coil of wires, which is called the solenoid, and it's very intense inside the magnetic field. And because we have so many loops of the wire, then we can assume that the magnetic field is really, really strong and uniform, especially towards the middle of the coil itself. The magnetic field inside the coil is moving from left to right. Okay, and so that's going to induce a very, very strong magnetic force. Okay, now I'm going to give you some equations, and so I'm going to introduce some additional concepts here. Okay, so here's our magnetic field. We denote that with a B. Okay, B is a vector quantity, although I'm just showing the magnitude here. I'm not showing the direction, so I don't have a vector sign on top of it. It's equal to mu naught, which is the permeability constant, which is 1.257 times 10 to the negative 6 Tesla meters per amp. Okay, so we're relating Tesla, which is magnetic field strength, to amps, which is current. Okay, and so we just take our permeability constant times the current in amps divided by 2 pi divided by r, which is the radius or the distance of that point away from the current carrying wire. Okay, so this is due to a straight wire. And what we'll want to do is we'll do a straight wire. We'll draw this as seen from their ends. Then the field vectors will lie inside the paper itself. So we can draw the field vectors in the plane of the paper. If we're drawing current loops, then it's best that we draw those in the plane of the paper. And then the field is, the loop center is perpendicular to the paper. Solenoids can be drawn either end-on with a field perpendicular to the paper, or you can see from the side where the field is in the plane of the paper. So, and if you have multiple sources of magnetic field, whoopsie. Okay, go back. Good job. Okay. If you have more than one source of a magnetic field, it's usually best that your drawing shows that the field vectors are in the plane of the paper. Okay. And then if you've got multiple fields, then you have multiple vectors. Okay. And so let's go ahead and apply this. We want to find the directions of the field due to each source, either a wire, a loop, or a solenoid, using the right-hand rule. Okay, so we find the direction first, and then we use the equation that we gave previously to give the magnitude of each field for a wire, loop, or a solenoid. Okay, and then we can, if we have multiple components, like if we have a wire and a loop, then we can just add those fields together using vector math, and then we can find the overall magnitude and direction of the magnetic field. Okay, so let's say we have 2 wires. Okay, so we have 10 amps in the first wire. We have an unknown current in the second wire, and we know that the magnetic field at B is 0. So we have no magnetic field here whatsoever. So what I'm going to do is, I think what I'll do is stop here, and I will segment this lecture so I can do some problem solving in the middle of it. And then once we've done the problem solving, then I'll move on to the next segment of the lecture. I'm going to do the problem solving with a camera so you can see it directly on my paper. Okay, so we'll stop here.